we're just gonna finish substitution today. And then I'm gonna show you maybe a little bit of polynomial division. It's not really, at this point, I don't know if it's in the curriculum anymore, to be honest. But it's something useful to know. It's just a computation trick. And yeah, we're gonna wrap it up with maybe what's called the main or the principal theorem of calculus, I think. I have to get back to you on the notation, but that's the plan for today. So we left off at substitution last time. And specifically, I showed you indefinite integrals. Specifically, I showed you the integrals that are not from A to B. They just don't have nothing there. So they look like this. Okay. Now I'm going to show you how to use it on the definite integrals. So just a fancy term for basically saying integrals that are from A to B. Okay. So let's take an example. The main, most of the procedure for substitution is going to be exactly the same. We're just going to have to change two more things, but I'm going to show them to you guys. So let's take integral from e to e squared of 1 x ln of x dx. Okay. Now, I think maybe this integral might work through by parts method, but it might be quite ugly, but I think it should work more or less. But that's not how we're going to solve it. We're just going to use a substitution. And probably, you know, to no surprise, we're just going to substitute this. So I'm going to say u is equal to ln of x. Okay. The next step is standard again. I'm just going to say du is equal to derivative ln of x dx, d of x here, which is just equal to du 1 over x dx. And after this, in the indefinite integral, what we used to do, we just plugged everything in the integral, replaced, and tried to solve it, right? When you're dealing with definite integrals, you have to change these as well, the heads of integration. So the idea is the following. X, in the original integral, x goes from e to e squared. So when x is equal to e, then my substitution, which is ln of x, is just equal to ln of e, which is 1. Right, so the only change in the definite integrals is that I have to change the heads of integration. Okay, so there's not much rocket science how you do it. You just take it by case. If x is equal to e, then ln of x by substitution is equal to ln of e is equal to 1. So this is u. And then if x is equal to e squared, I'm just gonna compute again. Ln of x is equal to ln of e squared, which is just 2, which is equal to u. Okay, so that is the only change. And now I can finally replace. So this is equal to integral. Instead of putting e, I'm just gonna put 1. Instead of putting e squared, I'm just gonna put 2. All right. Now, here I have x times ln of x. I don't know what x is, so I'm just gonna leave it in my head. Ln of x is u, and this is d of x. So this is, right now it's a mumbo jumbo. I have x and u there, so it's not okay. So I have to work it somewhere out. And what's bothering me? It's this 1 over x times dx. Okay, that's the problem. But luckily for us, I know that 1 over x times dx is equal to du from here. So just this is just equal to integral from 1 to 2 of 1 over u du. And right now, we know what this integral is. It's just ln of u from 2 to 1. This is just ln of 2. Okay. Now, an important difference from the indefinite integral is that I don't change back. Like once I get ln of u here, since I changed my heads of integration, I don't replace back with instead of u ln of x. Okay. Remember, if I were to solve the indefinite, so this is how you solve the definite one. Let's assume I just have to solve this. No heads of integration, x ln of x dx. Okay, let's assume I just have to solve this. I would proceed exactly the same way most of the steps. I would just say u is equal to ln of x. The whole du is equal to the partial. So du is just equal to 1 over x dx. And if I just replace, this is just integral from, unsurprisingly, it's the same integral, 1 u du. So this is just ln of u plus a constant. And now I have to replace. So I have to, because this is x and this is u, it just doesn't work out. So I would just write integral 1 over x ln of x dx is equal to ln of, instead of u, I plug in ln of x plus a constant. Okay. So now there's two methods. So if you want to, but it's definitely way more work like this, but it's up to you guys. You can compute the indefinite integral. So I just computed the indefinite integral, which is equal to this. And now I just say, hey, I want to compute this indefinite integral from, what was it, e to e squared. And this is just equal to ln of x from e to e squared. And if you were to plug these numbers, you would get exactly ln of 2. Which is the same answer I got here. So basically, what I'm trying to say is that you can either do it this way, which I find it to be safer and shorter, which is when applying substitution, replacing the heads of integration accordingly, moving from e to 1, from e squared to 2, because this is my change. And then once you solve it for u, you can just replace and compute it. Or you can just solve the indefinite integral, basically the same method, but you don't care about the heads of integration. And then once you get the final answer, you then just plug in the heads of integration. Okay? It's up to you, however you want to do it. I find this way to be shorter and faster, but if you're more comfortable with this, then go for it. Okay? Any questions on what I did here? Yeah.
So the absolute value when there's the rule of the
Oh, absolutely, absolutely. Yeah, I know. There's no absolute. Then there's no actual reason. Yeah, I should just put absolute value of u here. Of u here. There's no reason for that. Just I'm human after all. I make mistakes like you guys. So yes, great catch though. Any other questions on the method or what I did? Okay, I think we should take maybe another example of a definite one. Well, this is, we already did one, this. We've actually kind of exhausted, so I'm just gonna do, I guess, one of the integrals we did last time. Maybe it's it hits better the second time, but I'm just gonna make it definite. So I'm just gonna integrate from 0 to 1, x square root of 1 plus x dx. Pretty sure we solved the exact same one last time, but not with the limits of integration. So again, the whole idea is I'm just going to choose a u such that it's equal to 1 plus x. Then I'm just going to write du is equal to derivative 1 plus x dx times d of x. So du is equal to 1 times d of x. And now again, what's different is that I have to do the heads of integration. So if x is equal to 0, then I know that 1 plus x is equal to 1 plus 0 is just 1. So this is u. And the upper limit when x is 1, 1 plus x is equal to 1 plus 1 is equal to 2, which is equal to u. So again, this is the only thing that comes up new when you're dealing with definite integrals, is that you have to change the heads of integration. Right? It should make sense because I'm not looking if, I don't know, maybe you can picture it as a graph, but the graph is quite uninformative unless you're really comfortable with functions. But let's say this was my original function and I wanted this interval. Okay, remember I said that definite integrals compute the area under the graph. Let's say I want this interval from well, it's not 0 to 1, but let's just say it's 1 to 2. If I change my function, if I apply a change or a change of variables or a substitution, then if I keep the heads of integration, my interval might look way different than what I'm targeting. So that's why I need to adapt my intervals, my heads of integration here, in order to target the same area. This is, again, if you're not really interested in the explanation, nobody's going to ever ask you. Just remember that you do have to do this change. Now, let's just see what I get. I have integral. Instead of 0, I'm going to put 1. Instead of this 1, I'm going to put 2. So I've adapted my heads of integration. Now what is x? Instead of x, I can just write u minus 1 is equal to x. So I'll just write u minus 1 times square root of x of u. That was the whole idea, that 1 plus x is equal to u. And du is equal to dx, so I can just freely swap out. Yeah, and now I've changed my integral to only depending on u. So, and it's quite a well-behaved integral. We've done it before, so I can actually compute it. Let me actually compute it. Let's actually skip pages. I'm stuck with integral from 1 to 2 of u minus 1 square root of u du, and this is just equal to integral from 1 to 2 u square root of u minus, oh, forgot the du, minus integral 1 to 2 of 1 times square root of u du. And these should just be familiar formulas. 1, 2, I'll write like this so they look closer to what you know. Okay. Sorry about that. And for this, we should know the formula. We know that integral of x to the power of a dx is just x a plus 1 over a plus 1 plus a constant. So I'm just gonna plug it in here, and I get u. I'll write it in steps, I guess. One to two minus this is like something else. It's just a formula in case you forgot. Okay, and now I'm just going to plug in the numbers, and I'm going to get the result. Kind of the result, I guess. 2, 5 over 2 over 5 over 2 minus 1, 5 over 2 minus parentheses 2, 3 over 2, 3 over 2 minus 1, 3 over 2. Okay, and for all intents and purposes, I'm gonna leave it like this. There's nothing else for me to compute here. I don't really care to see that this is equal to, I don't even know, something like 2 point something. I don't know, but I don't really care what it's equal to. Okay, any questions on this substitution method? It's basically exactly the same, just that you have to have the small change, which is working with the heads of integration. That's the only new thing from the original substitution. So any questions on this? Or is it clear from last time? As clear as it can be, I guess. Because if not, I would probably just take the 20 minutes until break to show you what polynomial division looks like, or basically what the idea behind it is. It's kind of a good computation method. A little bit lengthy. I've personally never used it in my life, but maybe you guys will find uses for it. There are, I guess, other computation methods that I have used, but it's they're a little bit miss and match. So the idea is, let's do polynomial division. I'm just gonna use your knowledge on how you learned first time to divide things. Okay. First of all, I'm gonna define this because I think you actually get some problems along the way in which you're never told what a polynomial is. A polynomial is just a fancy term for a sum of powers. Okay. So basically, when you're saying that this is a polynomial of x, it's just a n xn plus an minus 1 xn minus 1 plus dot 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 a1 x plus a0. Okay, so this is how a polynomial looks. Basically, anything that's x to a power times a constant is a polynomial. Okay, so just to give an example, px of x is a polynomial. Px of x to the 25 plus 2x is a polynomial. You get the point. Every power of x is a polynomial. That's the idea. They just like this whole number. Now, the idea of polynomial division is to help you deal with stuff when you have fractions like this. X to the power of 3. Let me see if I can find like a good example. Yeah, this is fine. When you have integral of x to the power of 4, for example, plus 3x squared minus 4x squared plus 2x. I think I solved this somewhere else. Okay. So the whole idea of polynomial division is to help you deal with fractions that look like this, complicated, okay? So in this case, can you maybe do some smart substitutions to make it work out? Yes. Can you group stuff and like you don't need polynomial division if you observe that you can group the numerator nicely. But honestly, I don't know exactly how many of you can see it by looking at it, how it's going to split up. So polynomial division, what it does, it basically just helps you split it up. And you can think of it as how you used to divide numbers. Okay, let's try to take a trip down memory lane. What was it? If I wanted to divide 214 divided by 7, okay? Then maybe it's a bad number. Let's try 4. Let's try 4. Okay. How were you dividing? Just trip down memory lane. It was you can't divide 2 by 4, so I'm just going to divide this 21 divided by 4. That's 5, and I'm going to subtract 20, and I get 14 here. 4 and 14 goes in 3 times, and I get 12, and I get this 2 remainder here. Does this look familiar? I hope so, right? Like how you learned division when you were small? Because the same exact idea is going to happen here in this polynomial. Literally the same exact idea. So I'm just gonna, let's see exactly how I can write it in a nice way. So I have this x to the 4th, okay? So I have 1 here, x to the 4th. I'm trying to divide x to the 4th plus 3x squared minus 4. I'm dividing it by x squared plus 2x. Okay? Now, how many times does x squared go into x 4th? Well, it goes x squared, right? So now I have to subtract x to the 4th plus 2x times x squared, 2x to the 3rd. Okay. I subtract these. This goes away, and I'm stuck with minus 2x to the 3rd plus 3x squared minus 4. Okay. Now, how many times x squared and 2x to the 3rd? Minus 2x. So I do minus 2x times x squared. That's minus 2x to the 3rd. Minus 2x times 2x. That's 4x squared. And now let's subtract. This goes away, and I'm stuck with 7x squared minus 4. And I'm thinking for a second. And how many times x squared here? That's 7. So I have 7x squared plus 14x. If I divide this, this is going to give me, this is 0. This cancels out. So 0 minus 14x minus 4. And now, how many times x squared and 14x? No times, right? Because x squared is bigger than x. So it's literally just like division. But what's the idea? Why did I do all of this? Well, the whole idea is that I can write, if I look at what I did here, I can write x 4th plus 3x squared minus 4. I can write it as x squared plus 2x, x squared plus 2x, times x squared minus 2x plus 7, plus, what's the remainder here? I guess it's minus, but minus 14x minus 4. All right, that's the whole idea of polynomial division. It's literally just like the division when you first learned it. Now, why is this pretty good? Well, Now, coming back to my integral, if I just replace in my integral, oh, maybe I should have made this line much bigger. Something like that. Well, instead of copying this x4 plus 2 free x squared minus 4, I can just copy this thing. So I'm just going to copy this thing. And I get x squared plus 2x, x squared minus 2x plus 7 minus 14x minus 4. And now I hope you see it. The idea is that now I can just split this, and basically this cancels with this. This thing cancels with this. So I'm just writing it. So I'm just writing it as integral x squared plus 2x, x squared minus 2x plus 7 over x squared plus 2x dx minus integral of 14x plus 4 over x squared plus 2x dx. Okay. And now the whole idea of this problem was that I can now simplify x squared plus 2x here. And what I'm stuck with is integral of x squared minus 2x plus 7 dx minus integral of 14x plus 4 x squared. X squared plus 2x dx. Okay. And the whole idea is that this thing is a polynomial. We've done them in the first class of integrals, right? We know what that is equal to. And in this case, whenever you have a low power over a big power, it's usually pretty easy to solve. It's just an ln. You just got to figure out the ln for that, which isn't hard, really, as you get a little bit more experience. But this was the whole idea of polynomial division. After this, it's basically just me solving any other method I can find. Any questions on how I did the polynomial division? Which I did here. So any questions on this? Let me see if I actually have another nice example that we can do. Actually, I don't have any other example. I mean, I can create another example, but it's just going to be as ugly as possible. So the idea is the following. You just do it as you do normal division, right? As I showed you how to divide it here. 214 divided by 4. You just take bigger and bigger chunks out of what you have here. So in my case here, I started with the biggest power, x squared. And I asked, how many times does it go into x fourth? And the answer is x squared. Okay? I only care about the biggest power. At every step, I only look at the biggest power. So I took x squared, multiplied x squared times x squared, I get x to the fourth, plus 2x times x squared, 2x to the third. And I see what I get. x4 cancels with x4. And I'm stuck with minus 2x to the third plus 3x squared minus 4. Now I'm asking, how many times does x squared fit into x minus 2x to the third, it's minus 2x. Multiply minus 2x with this x squared, minus 2x to the third, minus 4x squared, divided, get this, repeat, and go over again. We can just take another example of polynomial division. I can let you think for 3 minutes. I'm only interested purely in the polynomial division. Anything else we're not gonna really do because we've done a decent amount of integrals. I'm just interested in seeing if you guys can do the polynomial division. Let's actually do some weird numbers. I'm gonna keep the same powers just because I don't want you to curse at me because I gave you too long of an exercise. But I'm gonna change the numbers that I have here. So I'm just gonna say 3x to the fourth minus x to the third plus 2x squared minus 1 over. Let's just try a simple one since you're doing it. I can't do it that way. Let's just do x plus 1. Dx. We'll just try to see how this polynomial division would work in this case. And after that, I'll solve it, and then we'll have a break. All right, let's try and do it together now. So whatever your status is, just look at what I'm doing, and try to follow what I'm doing. I'm going to try to go slow, just because I hate following other people's work myself. So. Okay, I kind of try to write it as big as I can so we can just go slow. So I'm just gonna take a normal division approach. X, how many times in 3x fourth? The answer is 3x to the third. So I do 3x to the third, multiply with this, and I get 3x to the fourth plus 3x to the third. Okay. See what I get? This cancels with this, and I'm stuck with minus 4x to the third plus 2x squared minus 1. Again, same answer, the same question, x in minus 4x to the third, that's minus 4x squared. Minus 4x squared times x is minus 4x to the third minus 4x squared. What do I have left after this? This goes away, and I'm stuck with 6x squared minus 1. Again, same old question. How many times does x go in 6x squared? The answer is 6x. It's minus. You're always like in the division example, you're always subtracting this thing. Okay, 6x squared, 6x, goes in 6x times, so this is 6x squared plus 6x. What do I have? This goes away, this goes away. I'm stuck with minus 6x minus 1. And lastly, x in 6x, that goes minus 6 times. Yeah, minus 6 times. And I get minus 6x minus 6. This goes away, this goes away. I'm stuck with 5. So the final answer for polynomial division is that this ugly denominator, 3x fourth minus x the third plus 2x squared minus 1 is equal to x plus 1 times 3x the third minus 4x squared plus 6x minus 6 plus 5. All right. And now, for example, I basically just multiplied this with this, and I'm gonna get 5 at the end. And now, if somebody asked me, okay, but this doesn't solve the integral, then I would just plug it in, and I would get, I'm just replacing this thing with what I have here, and I would get integral of 3x the third minus 4x squared plus 6x minus 6 dx plus the remainder, which is integral of 5x plus 1 e of x. And this, I hope everyone kind of knows how to solve by now. This is just 3x to the 4 over 4 minus 4x to the 2 over 3 plus 6x squared over 2 minus 6x. And this is just plus 5 ln of x plus 1 plus a constant. Okay. Again, in terms of formulas and what I used is just I just used the integral of x to the n dx is equal to xn plus 1 over n plus 1 plus a constant. And then integral of 1 x plus a constant dx is just the ln of x plus a constant. Let's put a actually here, a. Okay, so these are the formulas I used. We went through them in the first lecture. But are there any questions on the actual division that I did? As long as you picture that it's basically just division as you learned it in whatever grade you learned it, it shouldn't be that difficult. It is a little bit of ugly process, but it's pretty straightforward in terms of method. Okay, and it only comes it only comes to help you when you have to deal with these ugly fractions, when you have a higher power up top than you have down below. It just offers you a simplification, basically. Like integral of are you talking integral of f of x g of x kind of thing?
Yeah.
I don't personally know any of it.
Then you could just take the integral over the minus.
No, I understand, but it's you know, that's wishful thinking, right? No, I don't think there is. I'm almost fairly confident there's not. I know the only one that I know, but this is only for, it's not really a formula, it's just my, I guess my logic is that if f prime of x over f of x dx, this is equal to ln of f of x plus a constant, but it's nowhere near f over g of x. Right. So unfortunately there's not. That's why we're kind of developing methods for that. But great question. I wish there was, but I don't think there is, or I don't know it. Any other question on this method? Was it kind of clear to everyone how I got everything, the quotient and everything? And the logic is that when you have big fractions, they're bad. When you have polynomials like this, they're basically the easiest integral you can find. And you want to always kind of get to something that looks like this, because that's, you know, it's one line after that. But if there are no questions, we can just take a break now and we'll continue afterwards. Now that we're done with polynomial division, I will show you what's called the fundamental something theorem of calculus. Okay, that's what we're gonna see today. So fundamental theorem of calculus. Okay, it's quite short. It's not much to brag about. It's more about the notation, which I would rather, which is, as far as I know, gonna be in one of your mandatory assignments. And I would rather just explain it here to everyone rather than explaining it to everyone in particular, because nobody ever got the notation. So the idea is the following. We've worked with integrals up to this point that look something like f of t, d of t, right? We've worked with this type of integral, and we've worked with this type of integral, right? Now, I can define an integral that looks like this. I'm just going to define f of x is equal to integral from a or 0 or whatever number you want, a to x f of t dt. Right? Take in the notation, because this is the notation is going to be on your mandatory assignment. The representative, if you want to draw this here, let me show you how does this function look. So a small f, this is small f. This is small f. F of t, this is f of t. And let's say this is a. Okay, this is f of a. And now what this function is, you're basically just moving x along the way. And f of x, big f of x, is just this area over here. Right? So this would be x1. This is x2. Then, you know, this is f of x1. This is f of x2. Yeah, I mean, all of this is f of x2. I don't have my blue pen anymore, so I can't really help. Then if I have x3 here, all of this graph is f of x free. So that's how this new function works. And the whole idea of this introduction, this notation, is to basically claim the fundamental theorem of calculus, which says that if I take a derivative of this big F of x with respect to x, I'm going to get small f of x. That's all that the problem is saying. This is the fundamental theorem of calculus. The proof to it is quite simple, because if you just replace with the antiderivative here, and you take so let me a little bit complicate our notations. So let's stick. If you're interested in this, let's talk afterwards. I would be excited to. But just so it doesn't get complicated with notation, this is all that the fundamental theorem of calculus says. It doesn't say much, but basically, I could evaluate. I could just say that this f of x is equal to integral from 0 to x of et dft. All right. And what is this formula? What is this equal to? This e of t. What is this integral of e of t dt? Well, we've solved it many times. It's just e of t from 0 to x. So it's just e to the power of x minus e to the power of 0. Okay. So in the end, all this notation and everything just basically masks another function. Okay. There's nothing much to it other than notation. So just ask me if you guys didn't get the notation, because again, it is going to be on one of your mandatory assignments. Exactly this notation. So is it clear to everyone where the x comes in? The x, the variable, comes in here, not inside. Okay. In the happy case that your integral can be computed, like it is computed here, right? I can just say, I don't need to say anymore that f of x is equal to integral or whatever. I can just say f of x is equal to this. In the happy case that you can actually compute it, you can completely drop the integral and pretend it doesn't exist there anymore. Unfortunately, in your assignment, the problem will specifically say, do not attempt to compute the integral because you can't compute it. So you're not that lucky, but I'm just giving you general life advice here. So now that we've kind of done the main, the fundamental theorem of calculus, and there are no questions. Again, it's purely just a notation, and it's telling you this. That's all that you need to learn. Yes?
Might be unimportant, but the horizontal axis on the graph, is that only a t-axis, or is it also an axis of x?
Okay, so it's I'm a little bit confused by the question, and I'm trying to answer in a smart way. So here's the idea. This f of t here isn't an actual variable in itself. It's basically just showing you what you're integrating what you're integrating after. So I don't know, let's go back to how we defined our integral. I said that integral from a to b of f of t, let's say, dt. I basically just said that if this is your graph, and this is a, this is b, then this integral is just equal to the area under the graph. That's how I think I introduced definite integrals. Now, you're asking me if this graph is of t or whatever. And the way I would answer it is this graph here does show t. This horizontal line does show t. And A and B are just possible values of t. So in that regard, you can interpret that this is again t, and the x is just a possible value that the t can get. So yeah, that's the best explanation I can give you. That x is basically just values that t can take along the axis. Just as this a and b are values that t can get along the axis. Yeah. Any other questions on this? Because right now I am going to show you, I think, what I believe to be the ugliest formula in this entire class. And it's called, I'm actually gonna need a whole page for it. And I don't think I've seen it used in the exam necessarily. Or you could have used it in the exam, but it's definitely in the mandatory assignment. So this is called Leibniz integration rule. Integration rule. Okay, and what it looks at is, let's assume your integral looks like this: a, b. Let me try to write it somehow that it doesn't. T, d of t. Okay, let's assume it looks like this. This is the standard version. Everyone should be happy with it. Now, let's add another idea to it. Let's assume that this f inside also depends on an x. Okay? And no, I'm not going to show you double integrals right now or anything like that. Let's assume that this b depends on the x as well, and this a depends on the x. Let me give you an example. Instead of having the simple integral, which looks like integral from 0 to 1 of t squared dt, instead of having this simple integral, you just have integral from x squared to 1 plus x of x t squared d of t. Okay? Let's assume we have this. Now, Leibniz is just going to give you a formula, an ugly formula, but a formula for what the derivative of this integral is with respect to d of x. Okay? That is what Leibniz is going to give you. Which might come in handy at some points. I wanted to keep the f of t notation, just the d of t, just so because I've used it on the last paper, so I kept it the same. But I'm gonna have to struggle a little bit because on what I remember, the formula x and t are reversed. So I'm gonna do my best here. But as I said, if I take a derivative, for example, of this simple one, this derivative with respect to d of x, that's 0, right? This is 0. Why? Because there's absolutely no x there. X doesn't appear in that integral, so that's 0. On the other hand, when you have to take the integral of the derivative of this integral, you have x here, you have x here, and you have x here. So it's kind of messed up. Okay? We need to do something. And now let's write the ugly formula. I'm actually gonna use a whole page for this. So the derivative, I'm gonna write in the general case, and then we're gonna take an example. derivative of x, integral of a of x, b of x, times f of x t, d of t. So this integral is equal to, let me see exactly because it's a little bit troublesome. Coming back to your question when you asked me with is the values t's or whatever, just so we're clear, this is d of t. So x is fixed, but t can get the value b of x and a of x. So what I'm going to do is, if we wanted to write this in a completely naive method, I would just say, well, this is just the derivative of f of b, again, over d of x. This is just complete naive in your head, okay? Well, it happens that the formula is not that far off. It's in my head, I approximate this with f of x, instead of t, I put b of x, times the derivative of b of x with respect to x. So I know it doesn't look like much, but I'm basically just plugging in b of x. So that's why I'm just assuming that, hey, this is kind of similar to that thing. Now, the other part of it, it's similar to f of a dx, right? So in my head, this is just equal to minus f of x, a of x, derivative a of x with respect to x. Just so we're clear about it, this is just going in my head, and I'm just trying to give you an idea of how to memorize it, or why does it make a little bit of sense, okay? It's nothing like that, and don't write this part. If it helps you remember, write it on the cheat sheet, but don't write it on the exam. Okay? Not on exam. Okay? And now the last part is just a complete naive derivation. So naive, which is just plus integral, untouched, and you just take derivative of what's inside. And this is it. This is the formula for the derivative of the Leibniz. Don't worry, I'm going to show you an example. I'm losing my voice. Yeah, so it's minus, plus. Okay, let's just take an example, see how it works. Let's take a simple example, and then we're gonna complicate it as we go. Let's just take. This is fine. Let's just take. So, example. I'm gonna keep this close to me because I'm gonna show it to you guys a couple of times. Example. Usually, this kind of problem, or where Leibniz comes into play, is whenever you have, whenever you're given this value function or something like that, and they say, oh, the value function depends on some r and s that is equal to integral of something like that. I don't know, like, let's just put it br ar f of rs ds. You've already seen problems with value functions or whatever like this, and then they're asking you, what is the change if r goes from 10 to 100 or something like that? And this is that, if you have an integral there, it's a perfect case where you have to compute derivative of r S with respect to R, which is a classic application of Leibniz in this case. In this case, should think of Leibniz. Well, this is a classic example of where you should apply Leibniz. And this, in my case, I'm not going to try to overcomplicate the things. I'm just going to say, let's just compute the derivative with respect to, let's keep the same notation, x integral from 0 to 1 of x to the power of t of t. Okay. So let's assume I want to compute this. Well, let's apply the formula. So the formula basically just says I plug in, instead of t, I just plug in the big head of integration. So I just have x to the power of 1 times derivative of 1 with respect to x. Right, this is the first term. I'm going to write it right here. The first term is f of x bx times derivative of bx with respect to x. Right, this is this term. I'm going to write it like this. The second term is where I just plug in the lower bound value. So it's f of x ax derivative of ax with respect to x. And this is just x to the power of 0 times derivative of 0 with respect to x. Everyone on board with what I'm doing? So just for identification purposes, let me see if I can actually find. Found one. For identification purposes, this is a of x, this is b of x, and this is f of x t. And now let's slowly go through what I've done. So this is the first term, and f of x bx, I said is x1. So instead of t, I just plug in bx, which is 1. So this is just f of x bx. And then this, I have derivative of bx with respect to x, which is just, in my case, 1. All right. Now, the second one, let's start with this term. 0, this is a of x. So I have derivative with respect to a of x, or derivative of a of x with respect to x. Then I have f of x ax. So basically f of x0. Here it is. Okay? Basically just replacing step by step. And now plus the naive derivative, which is just integral b of x ax derivative f of xt dx dt. So what is it? I just plus integral of 0, 1 derivative of x to the power of t dx dt. Again, what I did here, this is just ax, this is bx, and this thing over here is just it's just f of xt.
There's two minuses, because minus and minus is plus.
Oh no, it's just when you skip the line, it's common to keep the same sign, just so you remind what it is. Okay, any questions on what I replaced here, or did it kind of make sense? Right now, the whole idea is that what's this derivative over here? what is this derivative over here? Derivative of 1 with respect to x. It's 0. This is 0. Derivative of 0 with respect to x, this is 0. So basically, that now you see that if the denominator, if the big head of integration does not depend on x, when I take the derivative, the first term is going to be 0. If a of x, the lower end, does not depend on x, when I take derivative, it's going to be 0. And I'm only going to be stuck with the naive derivative. So just to give it context, d of x of this ugly 0, 1 xt dt would just be equal to 0 minus 0 plus integral from 0 to 1 of that is just t x t minus 1 dft. Okay, and now if you just wanted to finish the whole problem, you would have to compute this integral. For my interest, I'm not really interested in showing you how to compute any more integrals for now, but rather just how to apply Leibniz. So I'm just gonna leave it at this for now. So there any questions on how I applied Leibniz here? This was a very simple example. The reason being is that this 1 does not depend on x, and this 0 does not depend on x. So 2 of my terms were just 0 after the first derivative. Now, if I just apply, let's just try to do a little bit more complicated example by saying derivative d of x of integral, let's just say from t to t squared. Sorry, from x to x squared. X to x squared of the same thing, just because we're kind of used to it by now. And I'm again going to apply Leibniz the same way. Again, I'm just going to write the formulas on the left so you can keep pace. I have f of x, b of x, derivative b of x with respect to x. Okay? What changes this time? What changes this time is my b of x is not 1. It's x squared. That's the only thing that changed. Okay? So now when I write it, f of x b of x is just f of x, in my case, x squared, xt. So I have, it looked kind of ugly, but we're never going to solve it, so don't stress about it. X to x squared, because t is now x squared, times the derivative of bx, so that's x squared, with respect to x. So again, instead of the 1 that I had here, instead of this 1, I just replaced it with x squared, which is my new bx right here. Now, when I write the f of x ax, derivative of ax, derivative of x, when I write it with ax, the same logic applies. But instead of 0, I'm just going to plug in my new ax, which is just x. So I have x to the power of x times derivative of x with respect to x. Again, just because this ax is equal to x from here. And lastly, I just have the naive one. which is just integral from x to x squared of the same thing, derivative of x to the power of t, derivative of x dt. Okay. And this is more or less done. I agree that these things look very ugly, but you don't need to do anything with them. It's already computed, right? There's no integral sign to them. There's nothing to them. All you can do now, if you want, just to finish it, is basically just compute these derivatives, which is just 2x and 1, and you're basically done. Okay, so in all itself, this Leibniz formula is only a formula that you might use in very niche situations. That's all there is to it. And I have no intention of proving it. The only thing I wanted to show you is how to actually use it and how to apply it. So if you have any questions on how to apply it, just go for it. Any questions on how I applied it or how I phrased it or anything like that? Yeah.
Why did you call it a naive derivative?
Oh, because so basically I just called it a naive derivative because in my head, when you're given where did I write the initial thing? When you're given this this formulation and you're asked for a derivative of x, the most naive thing would basically be to just take a derivative of what's inside and say call it done. That's the idea. That's why I called it a naive. Like for example, if I had integral from 0 to m of m x, I don't know, I'm just giving complete examples, dx. Okay, if you just had this and I asked you, okay, what's the derivative of this integral from x to dm, what's the derivative of this integral? Maybe if you're naive, you might just be like, oh, I'm just going to take a derivative of what's inside and call it done. That's why I call it the naive. But so you would just say wrongly that this is just equal to this, for example, which is not true, right? You need to apply Leibniz to it. But I mean, just since I already wrote it, for the sake of it, let's just apply it and see what we get. So m dx is equal to, as I said, this is just f of x a x. Well, in this case it gets a little bit more complicated because not complicated, but this function over here is function of x and m. This is b of m, and this is a of m. Again, so whatever variable you have right here, Leibniz only applies if you have to take a derivative of something that's not there. So in this case, if I had to compute derivative of with respect to x instead of m, I would not use Leibniz. I would just use the fundamental theorem of calculus. But this applies when you have to take a derivative of something else. That's what's there. Since I'm changing the variables, I'll actually do it right now with this change of variables. If you can follow it, fine. If not, don't really worry about it. It's kind of weird that I have to go with Leibniz, but you haven't actually done any integration problem in your seminars. So it's a little bit counterintuitive. But I'm just going to write the formula. And I get, instead of x, I put b of m. So I have m times m. derivative with respect to m minus, this is just m times 0, derivative of 0 with respect to m. Again, if you were to identify, this m is b of m, this 0 is a of m, and this is just f of m bm, f of m am. That's just some identification for you guys. And then lastly, it's your naive derivation, which is just d of x. Okay, so basically if you were just to do the naive derivation and you would get this, you would basically be missing on the first term, for example. That's why I call it naive derivation, that it's naive, it's incomplete. But again, it's something something much more niche than what I would say. I would much rather devote my attention to getting comfortable with by parts or substitution rather than this. Yes.
Can you just bump the paper down?
Oh, sorry. Like this? Yeah. Yeah, so again, I would much rather you guys spend the time on substitution or by parts, or if you're having trouble with not the polynomial division, but actually integrating polynomials, like integral of constant times x to the power of n, I would much rather get you comfortable with that rather than drill on this Leibniz, because 100% integrals are going to be present one way or another. Leibniz, there's a chance it's not going to be present at all, but integrals are 100% going to be present. And if you're kind of stuck on like the simple ones, you can't actually focus on the main ideas on the hard ones. So that would be my advice. Now, the last thing that I can show you on integrals, and you are officially done with integrals, is what's called improper integrals. Improper, so we had indefinite, definite, and now we have improper integrals. These are only just for cases that are undefined. Let me give you an example. Let's do integral from 0 to 1 of 1 over x, d of x. Okay, this is intrinsically simple. We've done it. You know that this is ln of x from 0 to 1. So this is equal to technically ln of 1 minus ln of 0. And here comes the problem. This thing is not defined. So whenever you're dealing with something that's undefined or just doesn't make sense, for example, I could have made the integral maybe to be 1 over 0, right? That's undefined as well. So whenever you're dealing with stuff like this, the common assumption is to say, okay, I can't compute ln of x from 1 to 0. It just doesn't work, right? ln of 0 is not defined, so it's impossible to compute. But what I'm going to say is, I'm just going to compute the limit when a goes to 0 of ln of x from a to 1. All right, so we're basically just replacing the bad values with just the limit that goes to them. This is all that improper integrals are. So basically, this would just be limit when a goes to 0, ln of 1 minus ln of a. And you know that ln of 0 is not defined, but you know that as long as when a goes very close to 0, ln of 0 goes to minus infinity. So I can just say that this is infinity. Okay, this would be a good way to show things. But this is all about improper integrals. Bottom line is, if something looks weird and you can't compute it, if you can't plug in the numbers because you can't divide by 0, or take ln of 0, or take a square root of a negative number or something, just write a limit that goes to that number. That's the whole idea. I guess you could have stuff like integral from 0 to infinity of x dx, right? If I just have this, I know I've computed this before. I know this is x squared over 2, 0 to infinity. And the idea is that I can't plug infinity. Infinity is not a number. So again, you just have to write it as limit when a goes to infinity of x squared over 2, 0 to a. Okay, that's the whole idea. You're basically just pretending that that's not infinity, is just a number that's going very, very big. Okay, so this is just limit when a goes to infinity of a squared over 2 minus 0. Obviously, this goes to infinity, so this is infinity. Okay. Now, the cases I'm giving you are very obvious, and if you had this on the exam, you would just skip this whole process and write infinity, I would give you full score for it. I wouldn't care for it. The problem comes if you have some more complicated thing there, a more complicated fraction that's not so obvious it goes to infinity. Then it's crucial that you replace. But if you get one of these cases, like if you got this, or if you got this and you just wrote, oh, that's equal to infinity, I would have been like, sure, makes perfect sense. Right? So I'm not talking necessarily about applying it for these easy problems, but rather when it gets complicated and you know you can't plug in numbers. But this is like very on a side note. Again, if you think you have problems with putting by parts in, or substitution, or just the simple regular integrals, I would definitely hammer that home rather than these technical details. Okay, but I think that's all for today. I'm losing my voice, so it's a great time to end.